So now let's take a look at some basic properties of probabilities. So remember that probabilities are between 0 and 1, and you can think of 0 and 1 as like 0% and 100%. So if the probability of an event is 1, then that means there's a 100% chance that that event will occur. So that event is certain to occur. But if a probability is 0, then there's no chance that event will happen, so that event is certain to not occur. But in general, probabilities have to be between 0 and 1, but could be equal to 0 or 1. But they can't be bigger than 1 or smaller than 0. So it would not make sense to say that a probability is 1.2 or negative 0.5 or something like that. It just doesn't make sense. And if I take all the probabilities of simple events and add them up, I have to get 1. The sum of the probabilities of simple events will always be 1. So if I think about flipping a coin, there are only 2 outcomes, heads or tails, and if I add up the probability of each of those, well, the probability of each of them is a half, and if I add them up, I'll get 1. So everything, if I add up the possible probabilities, I should always get 1. And there's one more term that we're going to need to use, and it's this word called the complement. And I want to point out this is spelled EM instead of IM. So if I give someone a compliment with an I, that would be saying something like, I like your shoes. That's different than the complement with an E. The complement is defined as all outcomes in the sample space that are not in A. So the complement of A is everything that is not in A. So if I draw a picture here, I might say, I'm going to use a circle for A. Let's say this is my set A. And let's say this is my sample space out here. The complement of A, which I like to use a little c, but our book usually uses like an apostrophe, so like A apostrophe, that is defined to be everything in the sample space that's not in A. So if I think about rolling a die, and my sample space is the numbers from 1 to 6, 4, 5, 6, maybe my event A is the numbers 2 and 3. The complement would be everything other than 2 or 3. So it would be 1, 4, 5, and 6. And then the complement rule right here is saying if I add up the probabilities of A and the complement, I have to get 1 because that's looking at the probability of anything in the sample space. It's saying first take the probability of A and then add the probability of A complement, but that adds up to be the whole sample space, and so it should add up to 1. And if you practice with our example right here, the probability of A would be 2/6, the probability of the complement would be 4/6, and these would add to 6/6, which is 1. And sometimes this complement rule can be helpful for finding a probability. Maybe it's really easy to find the probability of the complement or the probability of the set. Let's say it's easy to find the probability of the complement. Then I could find the probability of A by subtracting the probability of the complement from both sides. So it can be helpful for making problems simpler if I know something about the set or its complement. I can use that to find information about the other. So now let's look at exercise 9 here. This says, draw 1 card from a standard deck of 52 playing cards. And there's a link that I'll pull up where we can see a description of a deck of cards. So here is what a deck of cards looks like. You can see that there are 4 what are called suits. They're diamonds, clubs, hearts, and spades. And then there are aces, which are kind of like ones, and then the numbers 2 through 10. And then each suit has 3 face cards, Jack, Queen, King. And there are a total of 52 cards, and within each suit, there are 13 different cards. So part A says how many total outcomes are there in the sample space for this experiment. And this experiment is drawing a card from the deck. Well, there are 52 possible cards, so that means there are 52 possible outcomes in our sample space. So the next part says, what's the probability of drawing a face card? So I'm going to go down to the bottom here, part B. A face card, those are the things that are the jack, queens, and kings. So maybe the first thing to do is figure out how many of those there are. Well, within each suit, there are 3, a jack, queen, and a king. So there are 3 within each suit, and there are 4 suits, so overall there are 12 face cards. So to find the probability of getting a face card, I would do 12 divided by the total number of cards, which is 52. Part C says, what's the probability of drawing a card divisible by 3? So the first thing to do again would be to figure out within each suit how many cards are divisible by 3. So I would say 3, 6, and 9. And we're not going to think about face cards as representing numbers, and so these would be the only options. So within each suit, there are 3 of them, and again, there are 4 suits. So again, here we would have 12 possible options. So this would also be 12 over 52. The next part says, what's the probability of drawing a card not divisible by 3? Well, I could write out in each suit which numbers are not divisible by 3 and try to figure this out that way, or I could say, well, I could use the complement rule. I know how many are divisible by 3, and I know the probability of getting something divisible by 3. So I could say, well, the probability of getting something not divisible by 3, if I use that complement rule, would be 1 minus the probability of getting something that was divisible by 3. And if I made a common denominator here, I would have 52 over 52 minus 12 over 52, which would be 40 over 52. And so this would be my probability. Great, okay. Part E, if I go back up here, part E says, what's the probability of drawing a card that is a face card and a card divisible by 3? Well, we said that we aren't thinking of face cards as numbers, so there are no cards that are face cards and divisible by 3, and so here the probability would be 0 because it's something that's not possible to happen. Part F is worded a little bit differently. It says, what's the probability of drawing a card that is a red card or a black card? Well, any card is either going to be red or black. And so this probability will be 1 because no matter what, I will get something that is either red or black. If I had crossed this word or out and said and, there it wouldn't be possible to have something that was both red and black simultaneously, and that would change it to 0. But because it said or, the probability would be 1. And so hopefully this gives us some practice with some of these basic properties of probabilities. Next, we're going to see how to build on these a little bit and talk about slightly more complicated probabilities.